Hello students, welcome to Marine Engineering Tutorials. I'm Atul Kumar Gupta and I'm back with a new tutorial. Presently we are studying marine auxiliary systems. Various types of valves are an integral part of ship piping systems for controlling the fluid flow and to ensure proper operation and maintenance of the system. We will first learn about the purpose, construction and operation of screw down globe valve. Next we will explore the constructional difference between non-return and screw down globe valve. Then we will study the purpose, construction and operation of gate valve. After that we will discuss purpose, construction and operation of butterfly valve. Next, we will learn the purpose, construction, and operation of check or non-return valves. Then we will examine the purpose, construction, and operation of relief valve. Finally, we will study the purpose, construction, and operation of quick closing valve. Let us now go through each of these topics one by one in the following slides. Constructional details of screw down globe valve. A globe valve is used to regulate flow by throttling the pressure. The sketch shows the constructional details of a globe valve in order of its assembly. Globe valves are easily identified by their spherical body, usually made of cast steel. The valve body has two built-in flanges on the sides for connecting to the pipes and one on top for mounting the operating mechanism. The valve seat is attached to the body by screwing it in. In smaller valves, the seat is an integral part of the valve body. To increase the service life of the seat, its seating face is overlaid with steelite, an alloy of cobalt and chromium, which is known for its exceptional hardness, wear, and corrosion resistance. A cast steel bonnet, usually of the yoke type, houses the valve operating mechanism and is mounted above the valve body. A stainless steel spindle is used to operate the valve. The threaded portion of the spindle is inserted from the bottom of the bonnet and screwed into the yoke nut. A steelite faced steel valve disc is attached to the spindle using a pair of split washers and a nut. The valve disc may be made of stainless steel for general freshwater service or of bronze or gunmetal for seawater applications. The bonnet is secured to the valve body with studs and nuts with a fiber gasket providing the seal between the mating faces. A cast steel or gunmetal gland, usually in two parts, is secured to the bonnet with studs and nuts after the gland is packed. In the case of a single piece gland, it is inserted earlier during spindle installation. Finally, the hand wheel is attached to the spindle with a nut. The liquid entering the wall flows through the internal passage from bottom to the top and exits from the opposite end. As the liquid passes through the wall from inlet to outlet, it changes direction, resulting in a high pressure drop compared to gate or butterfly valves. For this reason, globe valve is not preferred on the suction side of pumps. They are usually installed on the delivery side of pumps or in locations where flow regulation is required. Compared to gate or drive valves, globe valves are bulkier and require more space for installation. Globe valves may be of screw down type or screw down non-return type with either a straight or angular flow design. Difference between non-return and screw down valve. This sketch shows an enlarged view of the disc and seat of a globe valve, illustrating the difference between screw down and screw down non-return valves. The valve seat is screwed in to the valve body. The valve seat guides the valve disc centrally so that the valve disc moves straight up and down. Around the valve guide, seat has several fluid ports through which the liquid flows. In a screw-down non-return valve, the spindle and disc are not connected to each other. The disc is guided to move up or down either by the seat guide or the spindle, although this sketch shows both. The disc is lifted by the force of fluid entering from the bottom through the fluid ports and is seated by its own weight when the flow stops or reverses. In a screw-down valve, the spindle and disc are attached together using a split washer and nut. The spindle has a groove to accommodate a pair of split washers, which act as a stopper. These washers are pressed by a nut screwed onto the disc so that the spindle and disc are held together and move up and down simultaneously. Gate valve. A gate valve should be either fully open or fully closed and is not suitable for controlling flow, as the void drawing action of the fluid can cause erosion of the valve seat and gate. When opened, it provides a clear, uninterrupted, full bore straight passage for the liquid as the valve gate is raised. This design offers the least resistance to liquid flow and is therefore preferred as a suction valve in large centrifugal pumps. The sketch shows the constructional details of a gate valve in the order of its assembly. The valve body is made of cast iron for general service and of bronze or gunmetal for seawater service. The valve seat is an integral part of the body, designed to accommodate the wedge-shaped gate and close the passage when required. The valve cover rests on top of the valve body and provides space to accommodate the gate when it is lifted. The wall body and cover have internal guides that ensure smooth vertical movement of the gate. The spindle has a collar that rests on the wall cover, maintaining a fixed vertical position. Unlike a globe wall, the spindle of gate wall does not move up or down. Instead, the lower part of the spindle has threads that engage with the gate, causing it to move up or down as the spindle is rotated. Usually, the gate is attached to the spindle with a removable nut. The gate has an internally drilled passage to allow the spindle threads to pass through when the valve is opened. The valve body, valve cover, and top cover are fastened together with nuts and bolts with gaskets inserted between the mating faces to prevent leakage. The gland is then packed to prevent fluid leakage around the spindle and is tightened using studs and nuts. The top part of the spindle has fine threads that serve as an indicator for the open shut position of the valve, as there is no other way to confirm whether the valve is open or closed. The top of the spindle is fitted with a hand wheel for operating the valve, which is secured in place with a nut. Butterfly valve. A butterfly valve is a type of flow control valve used in a ship's pipeline to start, stop, or regulate the flow of liquids such as seawater, fuel, ballast water, and fresh water. It is called a butterfly valve because its disc rotates like a butterfly's wing, turning 90 degrees from the fully open to fully closed, and vice versa. As the liquid flows through the straight passage with minimal resistance, it is often used as a suction valve for pumps where the net positive suction head is limited. Since this valve can also regulate the flow, it can be installed on the pump's delivery side as well. It occupies very little space and is easily installed between the two flanges. Butterfly valves are also commonly used on ships for remote operation via pneumatic or hydraulic actuators. A butterfly valve consists of a disc pivoted across the bore of a ring-shaped body, having the same radial dimensions as the pipe in which it is fitted. The sketch shows the constructional details of a butterfly valve in order of its assembly. The valve consists of a cast iron, carbon steel, or stainless steel body, depending on liquid to be handled. A nitrile rubber seat ring is fixed to the valve body, providing a seal with the disc edges when the valve is closed. A bonnet is secured on top of the valve body to house the valve operating mechanism. In smaller valves, the bonnet is an integral part of the valve body. Upper and lower bearings made of polytetrafluoroethylene are secured in the bonnet and valve body respectively. These support the shaft and permit smooth rotational movement. A stainless steel disc is placed in the seat ring to control the flow of fluid. A stainless steel shaft operates the war disc driven by an actuator mounted above it. Two O-rings are fitted into grooves on the shaft to prevent leakage between the shaft and the valve body at both the top and bottom. The shaft is then inserted through the bonnet, aligned with the disc and secured in place. Small valves are equipped with a lever and notch type operating mechanism, where the lever is locked in position by the notch to prevent unintended movement. Large valves are equipped with a worm and bonwheel mechanism, providing higher mechanical advantage to operate the valve against greater torque. The full bore straight through flow arrangement of this type of valve provides excellent flow characteristics and a low pressure drop, especially when designed with a carefully streamlined disc profile. The valve is quick acting, requiring only a quarter turn of the spindle to move it from fully open to fully closed positions. These valves are particularly useful for remote operation in ballast system, bunker transfer, and cargo operations on oil and chemical tankers. When operated with a linear actuator using air or hydraulic fluid as a working medium. Check or non-return valves. Non-return or check valves are installed in various pipelines to prevent reverse flow. The screw-down non-return valve discussed in the earlier slide, whose valve disc is not attached to the spindle, also falls into this category. This test shows two types of check valves, primarily used to prevent backflow. These valves have no spindles and therefore cannot regulate the flow. They open automatically under the pressure of fluid entering the valve, allowing it to pass to the outlet. The construction of these valves is described here in the order of their assembly. A non-return valve typically has a cast steel body, whereas a swing check valve generally has a bronze body and is commonly used in a ship's freshwater generator. These valves are usually small in size, with their seats forming an integral part of the valve body. In a non-return valve, the disc is guided by the valve body and moved upward under the inlet fluid pressure, returning to its seat by its own weight. In a swing check valve, the disc is pushed open by the incoming liquid around a pivot and swings back to the closed position in the absence of the flow. A stopper limits maximum valve opening. The top cover is provided for inspection and repair, secured by studs and nuts. A gasket is fitted between the mating surfaces to ensure a tight seal and prevent leakage. Relief valve. Relief valves are used to release excessive pressure in a pipe or pump when it exceeds the operating limit, typically set at about 10% above the normal working pressure. The sketch shows the construction of a relief valve in the order of its assembly. The valve body, made of cast steel or gunmetal, is designed for angular discharge of fluid to relieve excessive pressure. The body usually has an integral sheet formed during casting, which is finished by machining. A stainless steel stem or spindle holds the valve disc closed under the force of spring. When the fluid pressure exceeds the spring force, the valve disc lifts to release the fluid. The valve disc is secured to the spindle with a nut, and both the spindle and disc move together. The bonnet covers the valve body and houses the operating mechanism. The stem and disc assembled together are inserted into the bonnet from the bottom. The bonnet is attached to the valve body using studs and nuts with a gasket placed between them to prevent leakage. Packings are inserted around the stem and held in place by the gland to prevent leakage. Two long studs attached to the bonnet form the yoke. A spring plate is inserted through the yoke which rests on the stem. A heavy spring secured on the spring plate applies a force that keeps the valve closed under the normal working pressure. The top plate, together with the spring plate, hold the spring in position. Adjusting nuts are used to set the spring tension and are secured with lock nuts to prevent loosening. Under normal working conditions, the relief valve remains seated. If the pressure rises to the set value, the relief valve lifts and releases fluid continuously until the pressure drops again. Malfunction of a relief valve may be caused by incorrect settings, deposit on the valve seat, or damage to seat. Relief valve should be inspected at regular intervals. Quick closing valve. Ships, fuel oil settling, service, and storage tanks, as well as lubricating oil tanks located in high risk areas, must be fitted with valves that can be closed rapidly and remotely in the event of an emergency such as fire. Earlier ships were equipped with quick closing valves operated by pulling a wire from outside the machinery space. Modern ships are fitted with quick closing valves operated either hydraulically or pneumatically, offering greater reliability. We will see the construction and operation of a pneumatically operated quick closing valve. Position 1 shows the quick closing valve in manually closed condition where the tank contents are not in use. The valve is of the globe type with a bulbous body and a built-in seat. The bonnet is attached to the valve body using studs and nuts with a gasket between them to provide sealing. The valve disc is attached to the stem with a nut and the stem passes through the central bore of the bonnet. Upper part of the stem has left-handed square threads which are used to open and close the valve manually. A gland formed by the bonnet around the stem is packed to prevent leakage. Two long studs mounted on the bonnet form the valve yoke. The spring carrier rests on the corner of the stem and also indicates the valve's open-shut position. A heavy spring rests on the spring carrier and its force is used to shut the valve remotely. A guide bush attached to the upper part of the stem through left hand square threads is used to open and close the valve manually. Manual opening and closing of the valve is achieved by turning the hand wheel anti-clockwise or clockwise. The top flange has a half moon cap which is used to retain the valve in the open position by locking the guide bush. The half moon cam is activated through the operating lever, which is pushed up by the piston in the pneumatic cylinder when compressed air is supplied. Position 2 shows the quick closing valve in open condition when the tank contents start to flow out as shown. This position is obtained from the manually closed condition by keeping the operating lever pressed, which engages the half moon cam with a groove in the guide push and turning the hand wheel anti-clockwise completely until spring carrier indicates open position from shut to open. It can be observed that the stem rises up and spring gets compressed in this position. The valve is kept open while the tank is in use. Position 3 shows the valve in trip condition. To trip the valve, compressed air is supplied to the pneumatic cylinder which pushes the air piston, thereby moving the operating lever up, which disengages the half moon cam from guide bush and the spring forces the stem to close the valve disc. It can be observed that both the guide bush and stem have come down. To reset the valve again, hand wheel is turned clockwise until the end position. The guide bush will rise up and when the operating lever is pressed, the half moon cam again engages with the groove in guide bush, turning the hand wheel in anti-clockwise direction until the end position shown by the indicator opens the valve fully. Quick closing valves should be tested regularly to ensure the reliability of their operation. This helps reveal any defects in the operating mechanism so that they can be rectified in time. This completes the study of various types of valve used in ship piping systems. This book has been written by me and covers all the topics as per the Indian Maritime University syllabus. It explains key concepts using simple illustrations. The book also includes answers to all questions that have appeared in examinations conducted by Indian Maritime University. I am sure that the book will help students prepare effectively for exams and also support them in working safely with marine auxiliary systems. I hope you enjoyed the lecture. Feel free to share your feedback in the comment section. If you found this tutorial helpful, consider sharing it with your friends. Subscribe to the channel to stay updated with upcoming tutorials. I'll be back soon with a new lecture. Thank you for watching till the end.